This program takes a look at homologous series. I'd like to begin by looking at some of the features in a homologous series. And you can see an example of one that's shown here. As we move from methane to ethane to propane, this constitutes a homologous series. The first feature you should notice as we move from one to the next is you're increasing by the addition of a CH2 as you move from one to the next. So we've added CH2, making the chain longer. Now, even in the first case, if we look at the formula here, CH4 to C2H6, we can also see that moving from here to here, you've added CH2. So that's the first feature in a homologous series, is they differ by CH2. This is referred to as a methylene group. Another feature of a homologous series is they share the same general formula. In the case I have here, the general formula of these, so we've got that one and that one. Propane is C3H8, butane C4H10, and pentane C5H12. The general formula of this particular homologous series happens to be CnH2n plus 2. And you can see that that general formula will give you all of the formulas above. So they share a general formula. The next thing about a homologous series is demonstrated over here. Here I've shown the boiling points of the species, starting off with methane, which has 1 carbon, then ethane, which is 2, 3, 4, and so forth. We can see that there exists some sort of trend or pattern in their physical properties. I'd like to look at the pattern that exists here. Here we can see as the number of carbons increases, we get an increase in the boiling point. That happens because our molecules are becoming larger. That enhances the London dispersion force. These molecules are all nonpolar, so as we go from methane to ethane to propane, we move to larger and larger molecules, enhancing the London dispersion force. So I'll make note of that here. I'd like to add a little bit more to this description as well. As we move from methane to ethane, we're increasing it by 1 methylene group. That additional methylene group adds a 47% increase in the size of our molecule. And we get, from here to here, an increase of 73 degrees Celsius in its boiling point. The addition of another methylene group, however, gives a smaller percentage increase in size. Now the increase in size is only about 32%. And as a result, we get a smaller increase in the change in the boiling point. It only goes up by 47 degrees Celsius. And that pattern also continues. We make smaller and smaller increases to the percentage increase in size, and we get diminishing returns on the increase in boiling point. So it's not a linear trend. One more methylene group doesn't guarantee a certain increase. It diminishes as time goes on. But the trend is there, an increase in boiling point due to an increase in size. Now, the functional group can also have some effect on the properties of a particular homologous series. So here I started off with an alkane. Now I've moved to something which has a halogeno alkane, or a halogeno functional group. Now with this on the end, I recognize I've got a carbonyl group being added. Here, I have a hydroxyl group. And finally here, I have a carboxyl group. And in particular, a carboxylic acid with the presence of this. As we look at this, we can see as we move down in this direction from one to the next, we can see an increase in boiling points. The substances are also becoming less volatile. Meaning they're becoming more difficult to evaporate. That suggests we have an increase in intermolecular forces. Let's look at what some of those intermolecular forces are. Down here at this end, with our alkanes, we only have the London dispersion force at our disposal. Moving into the halogenoalkanes and the carbonyls group, we also now introduce some dipole-dipole interaction. And now, moving into our final members, with the presence of the OH groups, we move into hydrogen bonding. And you might recall, hydrogen bonding is the strongest of the intermolecular forces. So we can explain the differences in these different homologous series in relation to the intermolecular forces and the type of bonds they can make with each other. Let's apply what we know now to two review questions. Which of the following belong to the same homologous series as propanol? So first of all, let's see if we can find what the general formula is of propanol. First of all, its molecular formula. Well, this has got 3 carbons, 6 hydrogens, and an oxygen. That would then generate a formula, or general formula, CnH2n, so twice as many hydrogens as carbon, and an oxygen. Let's look at this one's formula. There are 2 carbons. There are 6 hydrogens and an oxygen. That doesn't work. If there are 2 carbons, our general formula up here predicts there should be 4. So that's not a member of this one's series. This actually has the same molecular formula as A, C2H6O. So again, it doesn't work. Our next molecule has 4 carbons in it. It has 1, 2, 3, 4, 5, 6, 7. It has 8 hydrogens and an oxygen. That does match our general formula. And our last one has 4 carbons and 8 hydrogens, but 2 oxygens. That doesn't match. So B is our answer. Now we're going to take a look at another question here that looks a little bit at solubility. And I'm referring here to the solubility in water. As we add a methylene group and we become a larger and larger molecule, what we're seeing as we move down here is we're getting something that's becoming less soluble in water. There's less of an attraction for water molecules the larger the molecule becomes. Let's take a look at why that's the case by looking at this first one. So this would be a 4-carbon molecule. With our OH group. And then there would be hydrogens here. I'll just go H2, 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 and H3. If we look at the structure of this, I'm going to kind of divide it in half. This portion of the molecule is very polar, and this portion of the molecule is nonpolar. The polar part of the molecule is attracted to water. The nonpolar is not. As we move down this table, the nonpolar size is essentially becoming larger and larger, whereas the polar segment of the molecule remains the same. So as we get to longer and longer molecules, the nonpolar aspect of the molecule tends to dominate, and we become less soluble. So that's it for a brief summary of homologous series. Thanks for watching.